Hi everyone, my name is William, and in this video I'm going to explore a question that bridges the gap between biological memory and artificial intelligence. Specifically, we are going to look at how your brain learns from the past to optimize the future, and we are going to propose an experiment to see if we can literally hack that process in real time. To understand the problem, let's start with something we have all experienced before, the coffee shop problem. Imagine you have just moved to a brand new city for a job. You don't know the streets, and you definitely don't know where to get caffeine. So in your first week, you explore. Let's say you find three options. Shop A is terrible, burn beams, room service. The second one is just okay. It's possible, but nothing really that special. And then hidden down the alleyway, you find a really nice coffee shop which serves absolute espresso perfection. At first, your mental map of the city is just neutral. You just know where these three places are, but very quickly, your behavior changes. You stop going to the bad shop entirely. You might visit the okay shop once in a while if you are in a huge rush. But you prioritize the route to the great shop. You start going to there almost exclusively. This seems simple, right? We do it without thinking, but computationally, your brain just did something miraculous. It didn't just store a static map of the city. Instead, it assigned a specific value to every location, to every coffee shop, and crucially, update those values based on your experience to maximize your future rewards. It built an internal model of the world. Okay, but how's the brain actually pull this off? For decades, neuroscientists have looked into a seahorse-shaped structure deep in the brain called the hippocampus. We know this is the engine of episodic memory and spatial navigation. Inside the hippocampus, there are neurons called place cells. These cells are incredibly specific. They only fire when you are standing in one particular spot in the world. As you walk across the room, different place cells light up in a sequence, literally drawing a map of your trajectory in the neural activity. But here's where it gets really interesting. The hippocampus doesn't just track where you are right now, it also predicts where you are going to be. This happens through a phenomenon called theta sweeps. When rat or human is moving through an environment, the electrical activity in the hippocampus oscillates at a rhythm of about 8 cycles per second, known as the theta rhythm. These theta sequences have been profusely studied in rodents' navigation linear mazes and found to sweep ahead of the path followed by the animal, and to alternate between possible maze arms or goal locations at choice points, leading to the proposal that they represent possible behavior alternatives to support goal-directed navigation. It is essentially a biological look ahead. 8 times a second, your brain is quickly simulating the immediate future, testing out the potential path before you even take a step. It's like a grandmaster chess player mentally moving pieces to see what happens next. But the brain doesn't stop working when you stop moving. When you sit down to rest or even go to sleep, the hippocampus shifts gears. The brain enters a state dominated by shockwave ripples. During these ripples, the place cells fire again, but this time they replay the trajectories you ran earlier in the day at high speed. It's like the brain is reviewing the game tape, consolidating those memories into a long-term storage. So, right now we have two mechanisms. The first one is the theta sweeps, looking ahead during movement, and the second one is the sharper ripples, looking back during the rest. Now, let's pivot for a second to the world of artificial intelligence. In reinforcement learning, or RL in short, we train software agents to solve problems by trial and error. To learn efficiently, these agents also use a form of memory. They store their past experiences, what stage they were in, what action they took, and what reward they got, into a database called the replay buffer. In the early days of the artificial intelligence, agents would learn by reviewing these memories randomly. But imagine trying to learn calculus by reading a textbook, but you just open a random page. You will read the introduction, then the index, then the random problem in chapter 5. It's incredibly inefficient. So, AI engineers develop a technique called prioritized experience replay. The idea is simple. Don't review the memories randomly. Prioritize the important ones. If an experience leads to a massive reward, like finding the perfect coffee shop, or a massive punishment, the AI should replay the memory more often. By oversampling the high-value experiences, the AI can learn optimal strategies dramatically faster. And this brings us to the core hypothesis of my proposal. If prioritized replay makes artificial intelligence learn faster, and biological brain use replay to learn, does it mean hippocampus also use the similar mechanism or algorithm to learn the same thing? Is your brain physically replaying the route to the great coffee shop more often than the route to the bum coffee shop? And if it is, does that bias in your memory directly cause you to make better decisions? Surprisingly, we don't fully know yet. We know replay is important, but we haven't definitely proven that it's systematically organized by value in this way, or that we can manipulate it. That's what we are going to test right now. We are proposing a matrix-style experiment to not just observe this process, but to interact and manipulate with it. We are going to build a closed-loop brain-machine interface, a BMI, that listens to these neural replays in real time and selectively reinforce them. Okay, here's the plan. We place rats in the virtual reality teammates. It's a simple setup. They run down a corridor and have to choose to turn left or turn right. But here's the catch. It's a probabilistic task. One arm gives a huge reward, and the other gives a tiny reward. Crucially, we switch which side has the higher reward across different sessions. This forces the rat to constantly learn and update its internal model of the world. While they perform this test, we will be recording from thousands of neurons in the CA1 regions of the hippocampus using high-density probes. Now is where technology gets exciting. We will train a deep neural network, an AI decoder, to read those brain signals. This decoder will learn to map the firing pattern of the neurons to the rat's position in the virtual world. Once it's trained, we can essentially see the rat's thoughts, even when the rat is standing still. If its brain generates a theta sweeps predicting a rundown to the left arm, or a sharp ripple replaying the path to the right arm, our computer will detect it and capture it instantly. First, in the aim number 1, we are simply going to measure the bias. We will calculate the sweep bias index. We want to see if right before the rat makes any choice, its theta sweeps are already voting for the high reward arm. We suspect that the brain is simulating the good option more often than the bad one, essentially priming the decision before the muscle even moves. But observation isn't enough. In science, if you want to prove how something works, you have to break it, or in our case, boost it. This is aim 2, the closed-loop prioritized replay brain-machine interface. We're going to set up a system that acts like a biological amplifier. The computer will be monitoring its brain waves to analyze the sharp ripples during brief pauses and inter-trial intervals. The moment the computer detects the sharp ripples, it will decode the content of that dream. It will ask, is the rat replaying the high reward path or the low reward path, defined as the replay priority index shown below. If the rat replays the high reward path, we immediately trigger a brief pulse of light, optogenetic stimulation, directly into the brain's reward or plasticity circuits. We are essentially giving the brain a biological thumbs up, artificially telling it, yes, keep that memory. That was the valuable sequence. However, if the red replaces the low reward path, we do nothing. We let the memory fade naturally. We will analyze the impact of the prioritized replay stimulation at both behavior and neural levels. Behaviorally, we will compare the learning speeds. In the neural aspect, we will recompute the replay priority index under the simulation and control conditions to test whether closed-loop stimulation increases the proportion and fidelity of the sharper repose events representing the high reward arm. We expect the high reward trajectories will be overrepresented in the theta strips and the sharper ripple replay, and that selectively reinforcing those events will further increase its priority, strengthen the prospective sweep bias, and accelerate learning of rewarded routes. However, you might question why this matters. Why go to all this trouble to make a rat, this little rat, learn a maze a little bit faster? Because it closes the loop between biology and technology. AI researchers develop prioritized replay to make computers smarter. Now, we are using this concept to understand how we, as human beings, can get smarter. It changes how we view the memory. It provides the mechanistic evidence that our memories are not just passive recording of the past. Instead, they are active, value-weighted simulations. Your brain is constantly curating its own library, highlighting the book that help you survive and succeed, and letting the others fade away. Furthermore, this informs the design of future neural prosthetics. Imagine a brain-machine interface that doesn't just help a paralyzed patient move a robotic arm, but also help a patient with memory loss prioritize and retain the information that actually matters to them. By leveraging the brain's own internal models, we could design the system that enhance learning and flexible, goal-directed behavior. And our brains have been optimizing these algorithms for millions of years. It's about the time for us to figure out the code. Thank you.